Today we're going to be looking at the topic of moles. So what is a mole? 1 mole is equivalent to 6.02 times 10 to the 23rd units, or atoms, or molecules. Just like 1 dozen equals 12, 1 mole equals 6.02 times 10 to the 23rd. Now let's look at molar mass. This is an important topic that's going to be discussed in the future slides. So molar mass is basically the atomic mass of an element. 1 mole of that element is equivalent to the molar mass of that element. So for example, 1 mole of hydrogen is equal to 1.008 as the molar mass of 1 mole of hydrogen. And 6.2 times 10 to the 23rd atoms is 1 mole of element. So basically, in 1.008 grams of hydrogen, there are 6.02 times 10 to the 23rd atoms. So, and if you want to find it in a compound, you basically just, like, for example, H2O, there's 2 hydrogens. So you would find the molar mass of 1 hydrogen, multiply it by 2, then add it to the 1 oxygen's molar mass, which is equivalent to 18. On dimensional analysis, we discussed this in the previous topic. Let's go over it again. So first, you put the unit you want with a question mark and equal sign. After that equal sign, you would put what is given, like the information, the numbers that are given, and then multiply that by what you want over what you want gone. Just cancel out the denominator. That might be confusing, but let me show you an example. Let's see, how many atoms of iron are in 1.50 moles of iron? So we want to find atoms, right? We put the question mark and the equal sign, then we put what is given, 1.50 moles of iron. So 1.50 mole times, and we want to cancel this out, so we put it in the denominator. And we know, as explained, 1 mole has 6.02 times 10 to the 23rd atoms in it. So we want to find atoms, that's why we put it at the top. So we multiply this, and this equates to 9.03 times 10 to the 23rd atoms. Similarly, let's look at some other problem. How much does 1.00 times 10 to the 8th atoms of gold weigh? So we want to find grams. That's one of the weighing measurement we will use. So we put what is given and cancel out the unit at the bottom. This right here is the molar mass of gold, by the way, on the periodic table. So I want to find this, and basically that equates to 3.27 times 10 to the negative 14th grams. If that was confusing, let me look at it again. We want to find grams, so we put grams at the top. We want to get rid of atoms, so we cross out atoms at the bottom. And this is the conversion factor. Let's do with compounds now. 18.0 grams of NH4 and 2Cl3 is present. How many moles of this substance does this represent? By the way, this 4 and 2 are subscripts. So the molar mass of this is equal to n times 2. Remember, the 2 distributes into here and here. So n times 2 plus h times 8 plus c plus o times 2. So basically, this molar mass n, molar mass h, molar mass c, molar mass oxygen, which equates to 96.09. Now we want to find how many moles does this represent. So we take 18.0, that's given, and this is the conversion factor. 1 mole is 1 mole of this substance is 96.09 grams, which is equivalent to 0.19 moles if you have 18 grams of that substance. Now let's discuss percent abundance. Percent abundance is quite literally the easiest thing in this entire unit. You just do the molar mass of the element divided by the molar mass of the compound it's part of, and multiply that by 100 to make it a percentage. For instance, let's calculate the percentage of carbon in methane, which is CH4. So first, the molar mass of carbon on the periodic table is 12. The molar mass of methane, which is molar mass of carbon, plus the molar mass of 4 hydrogens, so 12 times 1 plus 1 times 4 is 16. So we do molar mass of element, in this case carbon, 12, divided by molar mass of the compound, which is 16, times 100, which equates to about 75%, which means methane is 75% carbon. Now with this, we can use it in the empirical formula. So in the empirical formula, you would just take the percent abundance of one element and just convert that percentage to grams. Then multiply that by 1 mole divided by the molar mass of that element to convert to moles using dimensional analysis. Do the same for the others, then divide by the smallest mole value to find the empirical formula. Let me show you what I mean. So a compound is 50.05% sulfur, percent abundance of sulfur, and 49.95% oxygen by weight. So we do 50.05 and convert from a percentage to grams times 1 mole over 32.1 grams. I should put grams here. And we just cancel out the grams, and this equates to 1.56 moles. And we do the same for here. So 49.95 grams of oxygen times 1 mole divided by 16. Molar mass of oxygen is 16. That is 3.12 moles divided by the smallest mole value, which is 1.56, which means that in the empirical formula there is 1 sulfur and approximately 2 oxygens, so we get SO2, which is, by the way, sulfur dioxide. Now, molecular formulas are related to this. You just find the empirical formula, then they'll give you like a mass, a given mass, and then divide that by the molar mass of the empirical formula, and then multiply that result by each of the subscripts in the empirical formula. So let's take the same problem, but this time we're given the information that the actual molecule weighs 64.07 grams. So we found the empirical formula, which is here. So now we just find that sulfur in this empirical formula, there's only one of them, and the molar mass of 1 sulfur is 32.1, and the molar mass of 2 oxygens is 16 times 2, because 16 is 1. 16 times 2 is 32, so 32.1 plus 32 is, so the molar mass of this whole thing is 64.1. We divide that into the actual molecule's weight, and that is approximately 1. So we multiply the 1 by this S, and that's 1S, multiply the 1 by this O2, which is also O2. So the molecular formula is also SO2. Now the final subject in this is hydrates. So a hydrate is basically made up of an anhydrate and water. Water being H2O. So an anhydrate and water. So to first calculate for hydrates, you calculate the mass of the water and also the mass of the anhydrate. Then find the percent abundance of each in the mass of the hydrate. And then find the empirical formula using the steps we discussed here. And then we can get the formula of the hydrate. Let me show you what I mean. This is kind of confusing. So a 15.67 gram sample of hydrate of MgCO3, CO3 by the way, was heated to drive off the water. And that mass was reduced to 7.58 grams. So what is the formula of the hydrate? So we got that the mass of the anhydrate would be 7.58 because all the water was driven off after it's heated. While the mass of the water, which I was driven off, would just be this minus this, because you want to find like what was lost. And that would be 8.09. So 8.09 grams of water was driven off. And then we divide this by 15.67 to get the percent abundance of each, which is 48.4% of the anhydrate and 51.6% of the water. Then we use the empirical formula method that we did. So 48.4 grams times 1 mole divided by 84.3. 84.3 is, by the way, the molar mass of this. And then that equates to 0.57 moles. And then 51.6% of H2O. So the molar mass of H2O is 18. So 51.6 times 1 mole divided by 18 grams is 2.90 moles. Divided by the smallest, which is 0.57. So this means that there is one of these, and this means there are 5 H2Os. So the way we write an hydrate formula is like this. We put the anhydrate multiplication symbol, the number of waters here. In this case, 5 H2O. That was it. Thank you for watching, and a special thank you to Boucher for helping me with the problem in this unit. See you next time.